let's continue with quantization. With sampling, we obtain discrete time representation of the signal with real valued samples. But now for a digital representation, we need to convert them to discrete valued samples. That is, values that take values from numbers that take values from a finite set. So we do that by quantizing the values. Quantization is a mapping from continuous values to a discrete set of levels. It is an irreversible operation. Once you go from a continuous value to one of a discrete set of values, it's a mapping that you cannot reverse. So the choice of the levels and the choice of the regions of quantization will affect the loss, error, or distortion. Okay, so we will first consider scalar quantization. We will briefly touch upon vector quantization on a simple example. But of course, in order to get the most benefit out of quantization, vector quantization is used. Vector quantization means reading a bunch of samples and quantizing them all at once. Okay, let's talk about scalar quantization. Now, partition real numbers into n disjoint subsets, essentially, okay? Partition all of real numbers into n disjoint subsets. Of course, you may be interested on a very limited portion of the real line in general, depending on the range of values that your signal takes. However, it is, you can easily think of this as partitioning the whole real line. Okay, now construct these regions. R sub k is the kth region. Okay, so we're thinking about the real line, and we're thinking about regions R1, R2, etc. Okay, now everything, all the values x in the kth quantization region are going to be mapped to a particular value, xk hat. So in the first quantization region R1 here, all the values are going to be mapped to a particular value, x1 hat. Okay, and everything here is going to be mapped to x2 hat. So if x2 hat is going to represent this whole region, and x1 hat is going to represent this whole region. Of course, the price of paying infinity, mapping infinity to a given number of bits is going to be distortion. Why do we say number of bits? Well, because when we have n levels, okay, n levels, essentially we can represent each of these levels by choosing from n numbers, and this means using log to the base 2n bits per source sample. Because if we have log to the base 2n bits per source sample, we can represent 2 to the power log 2n levels, okay, with that many bits, which is n. Okay, so for n levels, we're using log n bits. Okay, so mapping an infinite number of possible numbers to n possible numbers is going to be distortion. However, provided we design this well, the distortion is not going to be important. Now, let's see an example of an 8-level quantization scheme. We are defining 8 regions. The first region is from -infinity to a1. All the numbers from -infinity to a1 are mapped into what? Let's call this whatever this level is. x1 hat. Okay. And all the numbers between a1 and a2 are mapped to x2 hat. All the numbers from a7 up to infinity are mapped to x8 hat. So there are altogether 8 different quantization numbers, regions. 8 quantization regions means 7 quantization region boundaries and 8 quantization levels. So we are describing how many numbers we are using to describe this quantization scheme. We use 7 numbers for the region boundaries, and we use 8 numbers for the levels. Okay, so if the number of quantization levels is n, we're using 2n minus 1 numbers. Okay. So we can represent quantization as a function. It's a many to one function, hence that's why it's irreversible, right? It's not invertible. It takes values x and maps them to x sub of k, x prime k. So q of x is equal to xk prime whenever x is in Rk. That is the functional representation of a quantizer. Now we can define distortion by the squared error. That is the squared distance from x, the value x, the actual value x, to the value that represents x. Okay? Now, quantization noise is the expected value of that squared error. Okay? So the expected value of x minus q of x squared. The expectation depends on the choice of quantization regions and levels, and of course the distribution of the source output. Okay. Now we define something called a signal to quantization noise ratio, SQNR. SQNR is given by the expectation of x squared divided by the expectation of the quantization noise squared. Let's take a look at the uniform quantizer. Uniform quantizer means all the regions are of equal size, except the 2 at the end, at the beginning and at the end. Okay. And all the quantization levels are also equal. So all quantization regions are of size delta, except the first and the last. Okay. But if the samples are taken in a bounded region, if the samples take values in a bounded region, then we need to only focus on a bounded region, then we can make all the quantization regions equal, including the first and the last. Now, if this is a 8-level quantizer, n equals 8, of course, we're going to use log to the base 8, which is 3 bits. And 3 bits, we can simply, very naively go from 0, 0, 0, 0, 0, 1, 0, 1, 0, all the way up to 1, 1, 1. Of course, in practice, we don't use this kind of mapping. We use things like gray coding, which we will study later on. But, you get the idea. You first quantize, and then you use log to n bits to represent the quantized values. So you have fully gone from an analog system to a discrete digital signal. Okay. Now let's try to do an example to understand distortion or quantization error. Okay. Let's consider a very easy case of a uniform quantizer with uniformly distributed input. As I said, the quantization error will depend on the distribution of the input signal X. Okay, suppose X is uniformly distributed. Okay, X has a PDF. Let me draw this better. X has a PDF, which is flat. Oops, not what I want. From negative A to A with value 1 over 2A. Very simple. Okay. Now, let's use a uniform quantizer with n levels. How big would you make the levels in this case? Well, if you have n levels, then you would take the interval from A to negative A and divide it into n even pieces, which would mean each piece would be of length 2A divided by n. So in this example, I've used 4 quantization regions, n equals 4, and I got, I used 5 quantization regions, okay? And I divided 2A into 5, okay? Now, how about the quantization levels? We can easily show that the quantization levels in this case should be the midpoint of the quantization region in which X lies. In other words, the centroid. Okay. So then, I mean, this is totally arguable by symmetry. Later on, we will discuss the general case. Now, the distortion, given that you are a value X in a particular region, is the square of the difference of X from the midpoint of that region. Okay. Now, if you think about X minus xk hat, what is the distribution of this random variable? Let's call it y. Y is x minus xk hat. X minus the difference from the midpoint of the region in which X lies. Well, X is equally likely to be anywhere in the region. So the difference from the midpoint should be uniformly distributed from negative to positive delta over 2. So the expectation then of y squared is given by y squared times, well, f of y dy from minus delta over 2 to delta over 2, and f of y is constant at 1 over delta. Okay, here it's done by substituting x for y. It's the same thing. And when we do this integral, you already remember this as the variance of a uniform random variable. It's going to be delta squared over 12. But you can easily see it by taking the integral. It's x cubed over 3 from minus delta over 2 delta over 2. So that is delta cubed over 12. times 1 over delta, which is delta cubed over 12, delta squared over 12. So that is the expected distortion. Expected distortion, or expected square error, or mean square error. Okay? We want to compute SQNR, for which we need the signal energy, or in other words, the expectation of x squared. And in this case, it's very simple, because you can easily see from this distribution that this is a uniform random variable whose range is 2a. So the variance, which in this case, since it's 0, means equivalent to the second moment, it's 2a squared over 12, which is a squared over 3. So if you don't remember these things, you may want to brush up a little bit on your basic probability skills. SQNR is then a squared over 3 divided by the mean square error, which is delta squared over 12, which gives us n squared. Interesting. The signal to quantization noise ratio for a uniform quantizer under uniform inputs increases quadratically with the number of levels. Okay. Now, what if we fed some other kind of input into the uniform quantizer? We know, we can sense that it's not going to be ideal. For example, if we feed Gaussian distributed inputs to a uniform quantizer, we know the input is not uniform. So we're not going to have all these, middle values represent the regions very as well as a uniform as they would in a uniform quantizer. Or we probably wouldn't want all quantization regions to be equal size, because there's more probability around 0. So those values are more likely. We would probably use finer quantization around where the Gaussian PDF makes a peak, right? However, for convenience, if we apply the uniform quantizer with Gaussian input, how would the distortion be? Okay, suppose the source x of t is stationary Gaussian mean, Gaussian zero mean random process with power spectral density that is limited to 100 Hertz. Okay. Now, sampling the source at Nyquist rate corresponds to sampling at 200 Hertz or more. Okay, and we want to apply a 3-bit uniform quantizer, 8-level uniform quantizer. The level boundaries, we have 7 of them. Suppose we place them at -60, -40, -20, up to 60. So 7 levels and 8 quantization levels. 7 boundaries, 8 quantization levels. What is the resulting rate and distortion? And can this distortion be improved with a different quantizer of the same rate with a different shape? Well, the answer, you can guess that it's yes. But first, let's try to compute this distortion. Now, first of all, we're talking about at least 200 samples per second, which corresponds to 600 bits per second with a 3-bit quantizer. All right, so what is the distortion? Distortion is the expected x minus x hat squared. Now, we need to, when we compute this expectation, we can easily use the total expectation theorem, right? basically, we can break down the expectation. Okay, so basically this is minus infinity to infinity, x minus q of x squared fx of x dx. But q of x depends on the region that x lies in. All right, so we can break it into, break the integral into pieces. Minus infinity to a1, x minus x1 hat squared fx of x, plus from a1 to a2, x minus x2 hat, and so on. So it's done here. Minus infinity to a1, x minus x1 hat squared fx of x, plus a1 to a2, x minus x2 x1 hat squared x2 hat squared f of x, plus a2 to a3, the same thing. So we can summarize all the terms in the middle, aside from the first and the last, as a summation, because they will have the same form. I minus 1 to a sub I, x minus xi hat squared fx of x dx. And how many i's do we have? I goes from 2 to 7. So 6 middle regions. And one region at the beginning, one region at the end. What is the region at the end? From a7 to infinity, x minus x8 hat squared fx of x dx. Now the rest is just doing the integration, because we know fx of x. Why? How do we know it? Well, we're given that it's a Gaussian. What are we given about it? We're given that its power spectral density is 2 within this region. How do you go from power spectral density to the variance of this Gaussian? Well, the integral of the power spectral density is the expectation x squared, right? Rxx of 0, which is 200. But that means that the variance let's see. Oh, I made a mistake. This is 100, this is minus 100, so the integral is 400. Okay, so the variance is 400. So we can write down the PDF 1 over square root 2 pi sigma squared e to the minus x squared over 2 sigma squared. Okay, where sigma squared is sigma squared is 400. When you do the computation, use MATLAB or some other tool, you find that the distortion is around 33.38. Is that good? Well, as a benchmark, perhaps we could consider, what if we use a 0-bit quantizer, meaning we didn't quantize at all? What would you do if you didn't quantize at all? Well, the Gaussian is centered around 0, so just transmit 0. I mean, you will be wrong in the positive side half the time and wrong in the negative side half the time. So you can hope that the errors are not too bad. With that, of course, the expected, the mean square error would be exactly equal to the variance, which is 400. So whatever quantizer you choose, you cannot do worse than this. This is the maximum distortion. If your quantizer is doing worse than this, then your quantizer is doing something terribly wrong. But the absolute lower bound that you can achieve with using 3 bits to quantize the source is 6.25. So the uniform quantizer does achieve better than nothing, but it is a little bit far from the absolute lower bound. So how can we approach this lower bound with the same number of bits? Well, you could either use vector quantization, meaning take several samples at a time and map them to a sequence of bits. I mean, a sequence of levels. Okay, so you wouldn't be using one bit sequence for just one sample, but you would be using a bit sequence for multiple samples. This is called vector quantization. Or you could use non-uniform quantization. Or alternatively, you could do something to the signal to make it more uniform, make it look more uniform. You know, do a transformation that is a reversible transformation, sort of expand the values that are changing fast and compress. So use a compression expansion algorithm, like an A low, mu low type characteristic. We will study this and then apply a uniform quantizer. Okay. Now, but first, think about what would happen if we applied an optimal non-uniform quantizer to the source. What do we mean by an optimal non-uniform quantizer? We mean that, okay, we have n bits. Okay, so we have 2 to the n levels. What is the best way to place these levels such that we will minimize the distortion? Okay, of course, we need to relax the constraint of equal quantization levels. We can do no worse than a uniform quantizer by relaxing the constraint of equal quantization levels. With n-level quantization, of course, we are going to choose 2n-1 parameters for our quantizer, for the levels and for the region boundaries. And this is the objective function that we want to minimize. Okay, for the given distribution on X. And this is not limited to the Gaussian case, this is general. For general distribution on X, if we have n levels, n-level quantizer. Oops. So the question is, choose the 2n-1 parameters, which are the region boundaries and the quantization levels, to minimize this expression for the given density function. Now, no matter what the density function, it's interesting that the optimization always gives us that the boundaries of the regions are equal to the midpoints of the quantization levels. Think about it. There are 2 quantization levels. So a number X is either going to be mapped to Xi hat or Xi plus 1 hat. This says that if so Xi hat, Xi plus 1 hat. Okay, this says that if the number, compare the number with the midpoint, okay, and if the number is closer to Xi hat, map it to Xi hat, and if the number is closer to Xi plus 1 hat, map it to Xi plus 1 hat. I mean, this is quite intuitive. Okay, because if you map it to something that is further, you would only be creating more error. Okay, so in an optimal quantizer, the boundaries of the quantization regions are the midpoints of the quantized levels or values. This is called the nearest neighbor law. And as I said, it doesn't depend at all on the distribution of X. It's a fundamental thing, nearest neighbor mapping. Okay, why would you not map a number to its nearest neighbor, right? I mean, otherwise you would only be increasing distance because we're using Euclidean norm. Okay, so furthermore, now this is the thing that is related now, is a function of the distribution. The quantization level, the ith quantization level, is the centroid of that region, meaning it is the conditional expectation of the value of X given that X is in that region from I-1 to AI. Then, I mean, note that conditional expectation is the minimum mean square error estimator. So the level Xi hat is the MMSE estimate of X given that X takes values from AI-1 to AI. Right? So if we do this optimization, if you use these levels chosen in this fashion for the Gaussian source, we obtain 13.816, which is a great improvement, and it gets us all the way to the rate distortion limit for 3 bits, okay, which is around 5. For better performance, of course, as I said, you could do vector quantization, which is done in practice. You take n samples at a time. You can think of these n samples as a point, as in n-dimensional space. Okay, you can visualize it for 2-dimensional and 3-dimensional space. For visualizing n-dimensional space, you need to be more creative. And then you imagine some regions that partition the space. Again, it's easy to visualize these regions in 3-dimensional space. Those would be the quantization regions. Okay, depending on how many regions you pick, you use that many bits. And the rate of quantization is log k over n, log to the base 2k over n bits per source output. Yeah. So in the two-dimensional space, we can see the constant Voronoi regions here. We are taking 2 samples at a time. So if X1 is a source sample and X2 is a source sample, and X1 and X2 fall into this hexagon, then I'm going to map them to the center of the hexagon. Now, notice that no matter what the distribution is, our criteria, nearest neighbor criteria, says the boundary between this point and this point is going to be in the middle. And the boundary of this point and this point is also going to be in the middle. The boundary of this point and this point is also going to be in the middle. So if the points are evenly spaced, then this results in hexagonal regions. Okay. Again, the dots are determined as centroids. The dots are determined as centroids. And the boundaries are determined by the nearest neighbor rule. And these are called Lloyd-Max conditions.